I'm Joyce Hornady. You might say accuracy is my business. I make bullets.
You are listening to the Hornady Podcast.
Thanks for joining us and enjoy the show.
Hello, everyone. Thanks for tuning into the Hornady Podcast. I'm your host, Seth, and today, a special treat, another episode of Quinlan's Corner. Our senior ballistician, Jayden Quinlan, on the show. Jayden, thanks for coming on.
Yeah, you bet. Been a little while.
It has been a little while, and just a couple weeks ago, we had the NRA show in Dallas, Texas, and mentioned this on another podcast, but amazing turnout. Texas always turns out for these shows. And at that show, a lot of people coming into the booth to express how much they enjoy the podcast, which is always rewarding to hear because this isn't necessarily part of your job, part of my job per se. I mean, we all have 40 or 50 hours worth of work to do every week, and this is something we squeeze in. So it's a labor, of course, but it's something we enjoy doing, and to interact with everybody there that enjoyed it, that loves to hear these episodes, and listen every single week. And every time someone came in, I would ask, what are your favorite episodes? What do you like to hear the most? And they all said, almost all of them said the same thing. I love Quinlan's Corner. So, it's unfortunate that we didn't have T-shirts at that. I feel like we could have made a killing just on the Hornady Podcast, Quinlan's Corner T-shirts.
Yeah, it's weird for me to hear all that. I'm not really a public person. I mean, you've known me for over a decade now, I guess,
yeah.
And don't really have social media or any of that kind of stuff. And so if it wasn't for the fact that it helped so many people, I probably wouldn't be willing to do it just because I don't know. I'd prefer to stay in my cave,
Yep. I don't, I don't blame you. Likewise, it's kind of moving, this is unrelated, but moving into marketing, now knocking on 4 years, certainly not my forte either. And I didn't have social media going into this job and was asked to get it for the job. I mean, you're the PR guy. Like you have to be kind of public facing, and it's nice to go back to your cave and put your head under the rock where you prefer to be. Yeah. But it does help a lot of people. And specifically these technical episodes have gotten a lot of traction where I think people see that we're reporting test results. We're reporting facts, math and science facts. And we're reporting what our testing has found. We're not telling anybody in a preachy manner what they need to do. We're telling them what we tested and what our results are, and taking those results and showing them what we do. And they can incorporate that at varying degrees into their own shooting. And I think people are seeing that. They recognize that, and it resonates with them. And I feel like the manner that we've luckily approached it, because, there was no track of here's what you do and how you do it. We just kind of, like we always do, just wing it. And it turned out that it was really well received. And again, coming back from the NRA show and hearing all the praise and some of the critiques and the criticism about what people want to hear and how they want to hear it, it was really gratifying. So with that, listeners out there in podcast land, the usual suspects, like, comment, subscribe, doesn't cost you anything, and it helps us out and it helps keep the podcast going. But more importantly, if you want a Quinlan's Corner t-shirt, you got to let us know. And the best way to do that is drop a comment. If you're watching on YouTube or listening on YouTube, drop it right here in the comment section. If you're an audio only, go ahead and send that in, podcast@hornady.com. If you want some podcast merchandise, t-shirts, your very own Quinlan's Corner sticker, let us know. We'd love to do it. And if there's enough need for it, I feel like I could see you on a truck window in the Sportsman's Warehouse parking lot.
This is terrifying.
Yeah.
After what I just told you.
Yeah. Well,
I can't have my
give the
face,
people
though.
what they want.
I don't want, if I get a say in this matter, which I feel like I should.
Yeah.
I don't want like the Bill Murray, T-shirt.
Oh,
right?
yeah,
With
right.
the face from
the chive,
Caddyshack or whatever.
Yeah.
None of that stuff.
I don't think that's necessary. I think maybe just a JQ stamp, something like that. The Q stamp of approval, which I've been talking about for over a decade now.
You have, yeah.
All right. Well, with that aside, let's get into today's episode. In today's episode, you wanted to talk about hit probability. And that really ties into so much of what we've already talked about. So you want to know, as a shooter, is what I'm seeing downrange, is it in the noise? Is it a problem? Do I need to make a correction? And can I make this shot? And what's my expected hit percentage? Those are good things to know. So hit probability is tough to understand because there's so many variables that go into it. So we're going to talk about the variables, and we've got 5 of the pipe hitting variables, the lion's share of the variables that are going to do the majority of your probability, and they relate to a lot of things we've already talked about. So before we jump right into the podcast, one, the listener should be familiar with our newly released drag variability reduction technology, the DVRT. We've put out a podcast about it. We've got some supplementary videos on that. Watch those, understand that concept. Again, this is a bullet design feature that we have patented, that we have implemented into our bullets going back almost 5 years now, 2018, 2019 timeframe, that helps reduce the variability in drag from shot to shot to shot to shot. So understand that. And then some other homework for you. As always, if you haven't, episodes 50 and 52, your groups are too small and your groups are still too small. And then episode 57 is a big one, which is the one hole groups, the podcast specifically about dispersion and that cone of fire and what you can expect to hit from that. So with that homework aside, assuming everyone's listened to that, let's dive into hit probability. And maybe we should start with, how would you define hit probability and how would you understand that concept to move forward to the things that influence it?
Yeah. So hit probability, breaking down the root words, I guess, hit is pretty easy to understand.
Yeah.
We have hits and misses, right?
Yeah. More misses usually.
Yeah. And probability is the chance of something happening. So it's just, what are the chances of you hitting this target?
I'm
Obviously,
more of
we're
like the
hitting a
1 in a
target,
million
right?
guy.
Yeah. Telling me there's a chance. So hitting a target, we bring target into it. That targets vary in size and they vary in location, right? Distance to the target. And so really your hit probability is the combination of all of those things. Your chances of hitting a given target size / shape at a given range under a given set of conditions. And the reason that we've kind of delayed discussing this topic, it's nothing new. We have a lot of internal analytics that we run on hit probability type stuff. But the reason we've delayed it this long is because you really have to lay the groundwork of a lot of the technical podcasts up to this point to have the understanding of these individual sources that we'll talk about for hit probability. But it's worth thinking about and worth digging into, because at a first level, hit probability gives you a very good troubleshooting ability. So as you said, is this in the noise or is there something wrong? And I've seen this in most shooting disciplines, where when something happens that we don't expect to happen, we're problem solvers. We want to find the source of that and fix it. So you're shooting and it's just kind of all over the place, and you find out your scope base is loose, or your scope is loose in the rings, or something very obvious. Action screws are loose in a bolt gun. You fix that and it goes back to performing the way you expected. That's a very obvious one. The issues that are kind of under the hood are all of these different sources we're going to talk about. And without understanding all of these, it's difficult to understand just the noise of the system. And when you get a result that's outside of your expectations, when the scope isn't loose, the base isn't loose, action screws aren't loose, there's nothing mechanical that's adding in variability. It's just a result that is experienced that's outside your expectations in your head, but the system is normal. You chase your tail.
Yeah.
And I've done it a bunch of times, less so now, with this level of understanding, but certainly have, and I've witnessed it countless times, and I still do. Every I mostly do long range shooting matches. I don't do as much. I've done pistol competitions and 3-gun and all that kind of stuff. And those things are still present. They're less magnified. So that's a lot of times why we talk about kind of the longer range stuff, because it magnifies all the concepts we're talking about in a way that in somebody's experience, they will have observed it. And so it's easier for them to connect those dots, although they're still present in shooting a pistol or whatever it may be. You just don't see them exposed as much. But I go to these matches and I see it all the time. People chasing their tails. And as problem-solving people, we're always going to assign some arbitrary reason for it. I pulled the shot. We've talked about that, right? Like know when you pull a shot.
Yeah,
it's quite obvious. But we'll associate some problem to it just because something bad happened and I don't understand why, and so I need to figure something out.
Yep.
And you see it in the form of, I just pulled the shot, and there's no like adjustments made or anything. You just kind of write that one off, right? I don't know what happened. I pulled it. All the way to the point of, well, my velocity must have changed. It must have migrated on me, so I'm going to adjust my muzzle velocity. Or my zero shift, my scope's not tracking. My zero, it didn't return back to zero. I got to recheck it. Or, fill in the blank of the reason. And in many, many cases, the equipment being used is very high quality equipment. I mean, the return rate on those optics is probably pretty low. Like they're a well-built scope. The odds of your zero not returning back mechanically because the scope are probably pretty low when you haven't like thrown it off a cliff, since the last time you shot it or anything, crazy. So if we can understand these sources, we can have a better idea of defining the noise in the system and avoiding chasing our tail. Because when you chase your tail, it costs you in 3 areas. Money.
Yep, there's a shot.
Because to stop chasing your tail, you're going to have to start pulling the trigger again, right, to reestablish a baseline you trust every shot. Time, the time to do that. And the other kind of hidden one is confidence.
Oh, yeah. Well, there's a fourth one, too. Points.
Oh, well, yeah, absolutely.
Points at a match, yeah.
Right. But the confidence one really, it's eaten me up before. There's nothing like having a total lack of confidence in your system. Like your performance is just going to tank.
Yeah. The mental geometry going into something competitive is huge.
Mm-hmm.
Yep. And a prime example of what you just talked about that I've witnessed as well on long-range targets where the time of flight is really long. Let's say I witnessed this at FTW. Luckily, this wasn't in competition, but it was people shooting the 7PRC, 180 ELD matches. That bullet is just a juggernaut.
Mm-hmm.
And the target distance was 1,800 yards. And your ability to shoot a group, and this given shooter, his ability to shoot a group at 1,800 yards, at best, he's going to shoot an 18-inch group.
Yeah.
And that's if everything's perfect.
Mm-hmm.
And the target was 36 inches square, and there's crosswind. It's over a mile away, and he's trying to make 1 to 3/10 of a mil corrections for elevation and windage based off one shot.
Right.
And your ability to shoot a 1 or 2/10 of a mil group at that distance is virtually impossible.
Mm-hmm.
And you're making corrections, and he was just chasing his tail. And he got some on the steel.
Right.
And then, there it is. I got to do that same hold. But the reality is the cone of fire was just such that you were making corrections that had you made no correction, you would have been back on the steel. But you made what you thought was the right correction, and now you're off.
Mm-hmm.
And that's just, it was a loop. Next thing you know, that barrel is as hot as a welding rod, and it's time to hang it up.
Yeah.
So definitely a spiral downward when you start doing some of these things.
Mm-hmm. Yeah, and good descriptor there is the cone of fire part. All too often we think that the bullet's going to go right where we aim.
Yeah, it's a laser beam.
Right. Yeah. If we're shooting laser beams, you're in pretty good shape. But you have a cone of fire. Things are going to happen within that are randomized and not within your control. So.
Absolutely.
The Hornady Click Adjust Bullet Seating Micrometer. Precisely set bullet seating depth with Click Adjust in 1/1000th of an inch increments and easy to read graduations. It's a quick and easy way to achieve bench rest accuracy and consistency with tactile clicks, just like a Click Adjust scope turret. Easily installed on Hornady custom or match grade seating dies. Take your reloading game to the next level. with the Hornady Click Adjust Bullet Seating Micrometer.
The other thing that hit probability is beneficial for is it allows you to make smarter decisions on the gun. So there's many instances to that point, the FTW example, where you should not vary your point of aim. You should leave it in the same place. And there's enough noise in the system that you're just playing the lottery, right? You're just sending samples till you win. Because once you go start changing, you're chasing your tail to your specific example. So from a troubleshooting standpoint, it's very beneficial because it can allow you to figure out what's wrong quicker. Because you understand what is within the noise and what is without.
Mm-hmm.
And when you get things that happen outside of the noise, then you can troubleshoot to find the root cause of that problem more quickly. And then obviously to make smarter decisions on the gun. So we have 5 different sources we're going to talk about. Muzzle exit, which we talked about in what episode was it?
That was number 57,
57.
the podcast solely about dispersion. We named that one hole groups.
Yeah. So I won't go into too much detail there, but
Okay.
but a little refresher. The shooter, ourselves, the human, right? I think we talked about that a lot in that
The
one
nut
too.
behind the bolt.
Wind,
Never heard of it.
never heard of it either. Velocity and drag. So those are your 5 different sources. We're going to talk about how all of those, where they have an impact, how much, and then how they all come together to give you your total.
Yep. And then stack. This one adds and this one subtracts, and then this one, it gets pretty messy. So we'll walk through these 1 through 5, starting with muzzle exit. So that's when that bullet uncorks the things that you really have no control over, essentially. I mean, you have some control of what kind of chamber does it have and the throat dimensions and the concentricity on your rounds and stuff like that. But largely, you pull the trigger, what happens is out of your control in regard to muzzle exit.
Right. Yeah, this is why not all bullets go in the same hole, even at short range, 100 yards. So in that podcast 57, we had discussed stuff like center of gravity offset of the bullet, where the jacket concentricity is never perfectly perfect.
Right.
It's manufacturing, right? You're moving material and you're modifying it. And so if the jacket is a little bit thicker on one side of the bullet than the other, that takes your high density lead core and shifts it off to one side a little bit. And so the center of gravity of the bullet is not necessarily aligned with the center of form or the center of shape. And we described that, I think, as
Out of balance tire.
Out of balance tire. That's right. So the farther the center of gravity gets off of the center of form or the center of shape, the worse the wobble of a tire would get, right? The more out of balance tire is, the worse it gets. The faster you spin it, the worse the wobble gets. Similar concept to that.
Yeah. And with modern manufacturing and with modern match grade bullets from virtually anybody, that's a really small concern, but it's still present at some degree in every bullet ever manufactured.
That's
generally.
Right. Yeah. And you can still have it even with like lathe turned monolithics. A lot of people will go to that and say, well, there's no jacket to be not concentric. It's a monolithic material. It's all the same. You can still have it there if there is variable density to the material itself that you're making the bullet out of. But anyway, but the fact that exists, and the reason that you get the randomized dispersion, so some shots go a little high, low, left, right. If you shoot enough shots, if your sample size is high enough at short range, your group will form a circular pattern. That's another good indication of, is your sample size high enough? If you shoot a triangle-shaped group, or it's strung vertically or horizontally, or at any angle it has like a line form to it, your sample size isn't high enough to capture the true dispersion, the cone of fire of that system. But the reason that it's all randomized, why some go high and left and right and everywhere in between to form essentially a circle, is because where that center of gravity is offset when it first comes out of the muzzle is going to dictate where that bullet ends up going.
Right.
And the fact that you don't have any control of that, you don't know the center of gravity offset of your bullet, and you can't clock it. If you could, which we've done this, you take a bullet and you induce a known amount of center of gravity offset and you clock it into the same position every single time, it'll essentially go to the same place every single time.
Right.
And if you change the clock orientation, you change where it goes.
Yeah. I've seen the test results and the targets, and that's pretty cool that you could you had 4 separate groups, which was
Mhm.
pretty neat.
Yeah. Yeah, you can make donut bullets that way if you really want to mess with a buddy. You can make bullets that will never shoot in the center. They just shoot a big donut.
Yeah.
But anyway, that was the center of gravity offset piece. Principal axis tilt or inbore yaw. Again, that's where the bullet can be crooked.
In the bore. It's
Yep.
trapped
Right.
by the rifling,
Yep.
and it's trapped crooked.
Yeah.
And there's no recovering that.
No,
No.
not really, unless by chance it hits a portion in bore that's larger dimensions and can kind of straighten itself back out somehow. Not
No.
likely.
No.
So anyway,
And this can happen as it enters the forcing cone. As soon as it uncorks from the case, it can be crooked.
that's right.
And that's why Hornady, if you look at all of our cartridge designs, that's why we have a very specific throat geometry formula, essentially, is to help reduce that initial principal axis tilt. But this can also happen somewhere else down the barrel.
Mm-hmm.
If you've got a slightly larger diameter of some spots in your barrel, this is more common in, say, a button-pulled barrel or something like that, where you have a slightly larger diameter, and we're talking tenths of a thou here.
Right.
And that bullet being propelled can get ever so slightly crooked.
Yep, and at the muzzle.
Yeah.
Which is the worst place for it to occur.
Mm.
But it functionally, it's very similar to the CG offset in that you have a randomized orientation. So let's say the bullet is tipped in bore. You don't get to control which way it's oriented, which way it's pointed, and by how much it's tipped. And so you have variability in both CG offset and in bore angle, and the variability is in the amount and the orientation of it at muzzle exit, and that's what influences where the bullet will go. So again, that's why dispersion at shorter range is a randomized, shots just kind of populate in there. And the population is, for those a little more statistically savvy, the shot radius, so the distance from the mean to where the shot lands, is not normally distributed in the majority of especially precision rifle stuff. And so when we talk about distribution profiles, the normal distribution or the Gaussian distribution is kind of that bell curve shape.
Yep.
It doesn't necessarily do that, particularly with precision systems. It follows more of a Weibull or a Riley distribution. In simple terms, so we call it the section volcano. So
Okay.
So if you took a volcano and you cut it in half and we're looking at it from the side, and you looked from the center of the volcano, right? You have the crater on the top.
Yeah.
And from the center of that crater, it kind of ramps up to the edge of the volcano, and then it falls off, down the slope of the mountain of the volcano.
Mm-hmm.
That's more so what the distribution profile looks like on precision rifle stuff.
More in the center than on the edges.
Yeah, more just off of the center.
Okay.
Yeah, because you're talking about the radius, right? So
Right.
from center, what are the number of shots as you move out? And so that's an interesting thing, because there's many parts that we'll get to, like velocity variation and drag variability, where they are normally distributed. So the standard deviation that we talk about a lot, and we will talk to here, is very useful there. But when you're talking about dispersion, it's not necessarily the normal distribution.
Okay.
So anyway, so you're starting with that. That's your baseline. And let's say that you have a 1 minute rifle at 100 yards, and that's like actual valid
For
sample
100
size.
shot.
Right. Yeah. Let's say 20 plus shots. It's a minute of angle. That grows slightly greater than linear as a function of time or distance, right? We usually think of shooting in terms of distance, although time is what's really mattering.
Mm-hmm.
So let's say that 1 inch at 100 yards extreme spread group size is going to turn into, at 1,000, if it was perfectly linear, it would turn into a 10 inch, right? Because it's 10 times the distance. It's going to be slightly worse than that. But this is your starting baseline. So everything else that we talk about after this is just adding to the
Potential.
It's adding to where the bullet ends up. So you're starting with that,
Mhm.
right?
That's your
let's
baseline.
call it the baseline cone of fire from a muzzle exit standpoint. So then we can move into the second source, which is the shooter.
Largely the biggest source sometimes.
Sometimes it is, yeah. And so muzzle exit is a randomized direction, right? We talked about that. Like,
Yeah, but you don't get to pick.
Yeah, you don't get to pick. You don't get to know unless you deliberately control it. But the shooter is also randomized in direction. So the shooter would be things like aiming error. We're humans, and our ability to perceive something optically or visually and repeat it back to the exact same position. So your reticle on target, putting it back into the exact same position. Certainly there's a gradient there. Right?
Yeah, some are really, really good.
If you have a gridded target with or some sort of very precise reference point, you can repeat back to that quite precisely. But then you have stuff that's like an animal during hunting, right? You're looking at a hide or a steel target or whatever it may be, something that's not real descript.
Right.
You're likely going to have some variability every time you aim at that. So that's built in, but it's usually randomized in direction. Recoil management can be a part of that.
Sure.
Probably not as much as a lot of people think. I remember thinking in my younger years, the rifle has to recoil the exact same way every single time, or your shot's not going to go where you want.
Right.
And then you look now and you can take a rifle and lay it on a sandbag and not even touch it with your shoulder and let it go where it's going to go and have some pretty good success with it,
We've all hit some targets at some pretty remarkable ranges with some pretty remarkably small target sizes doing free recoil off tree stump, rock, you name it, barricade. Yeah, you throw a 10-pound sandbag up there, wiggle in your 20-pound hot rod 6mm and free recoil it. And man, it's remarkable how accurate you can be.
Yeah. So it kind of goes back to the old argument of how much is the system moving before the bullet leaves the muzzle.
And I suppose with a bigger Magnum, obviously that's going to be a little more sensitive.
Yeah, lighter rifle, more recoil. Yeah, absolutely. So varying degrees there, but it can happen and it's kind of randomized. Another randomized error is cant. It's randomized more so in the amount of cant you get. There's probably variability there. So you'll see guys that run a bubble level or some sort of electronic level.
Yep.
That's an attempt to mitigate the variability in the cant. So what it allows you to do is try to return back to the same amount of cant. Optimally, it's no cant, but if there is some cant, right,
At least
as
it's
long
repeatable.
as it's the same every single time, this will cause shots to go left and right. A little bit of elevation will be built in there too, but initially it's mainly left and right type stuff, and that's because the line of sight optic is mounted directly above the bore, and so any tipping or canting of the rifle is going to change the orientation of those two to each other. But cant can be kind of variable because just shot. It's not going to be identical. Parallax can be a big one if your optic isn't adjusted correctly, depending on your head's position and the image you see. You can, you'll see a lot of guys lay behind the rifle and kind of move their head back and forth or side to side, as they're adjusting their parallax to try to tune that out to get it to go away, so that as soon as you have your head in an improper position, the eye relief begins to show up and kind of give you an indication that you're not in the same position you were in before. Then you have our old friend Mirage, which is a nightmare.
It can be. I just shot in Tennessee at K&M for the first time a month ago. Number one, I've never shot in a no-win scenario in my entire life until that day.
Yeah.
Which was really unusual. I mean, I was asking people, like, is the wind really not blowing at all?
Yeah.
It was really bizarre to me. But two, in the morning, the Mirage was, it was intense. And you'd think you're looking at a clear image, but everybody across the board was 2/10 low on their dope, but there wasn't any other problem other than that's a Mirage. It'll go away about 10 a.m. And until then, you're going to have to adjust 2/10.
Yeah.
It was pretty remarkable. One, that it was that consistent, but two, I'd never quite seen it that bad or shot in no wind, which was wild.
Yeah.
But Mirage can be intense.
Yeah. It's easy to forget that we're looking through an atmosphere, and an atmosphere has density. I always like to, the biggest reminder for me is when you see the sunrise or sunset or the moon, when it's down on the horizon, it's huge. It's like magnified.
Yeah. Yep.
And as it gets higher in elevation in the sky, it gets smaller, and it's not changing size. That's from the magnification of when you're looking straight across the horizon, you're looking through higher density air, and there's a magnification kind of that takes effect and causes that to be bigger. We think about that in the concept of how far away we are from the moon or the sun, looking across the entire horizon, right, that you can see line of sight wise. And when we're shooting a target at 1,000 yards or whatever, it's nowhere near that. But that principle still exists. And obviously, Mirage does a good job of displaying that to us as that image is distorted. And there's nothing worse than laying behind a rifle and looking at the target and just watching it bounce around and dance.
That's a poke and hope scenario.
So which one do I aim at?
And I'll send one and see what happens.
Yeah, absolutely.
The Hornady Rapid Safe Keypad Vault offers quick, dependable access to your firearm while providing security from unauthorized users. The Rapid Safe Keypad Vault is constructed of a heavy-duty 14-gauge steel housing and thick steel lid for tamper-proof security. The included RFID watch band tag and RFID decal can be selectively programmed to open this safe and any other Rapid Safe you own. The Rapid Safe Keypad Vault from Hornady Security.
And then what I'll say is the last shooter error contribution that we're going to list here, not that there's not more possible, but is zeroing errors.
This is a big one.
That's the big one. That's why we left it for the last part.
Yeah.
And back to the sample size stuff again. We've learned over the years that, like myself, I will not zero a rifle with less than 20 shots.
100%.
And I'm not laying down ripping off 20 in a row. I think I've said before, the way I do it is I take the average use case of that rifle and I use that as the method to zero it.
3-shot, 5-shot, 10-shot,
whatever it may be. Yeah, my hunting rifle, I do 3s, and then I let it cool off, and I come back and do it again, just like I would do in hunting. If it's a competition rifle where I might be shooting, 10 or 20 shots within a time frame, I conduct it that same way.
Right. And then you just do your composite group.
Mm-hmm.
Yeah. So your hunting rifle would be 7 3-shot groups for a 21-shot aggregate.
Mm-hmm. That's right. But the reason that zeroing errors are so important is all too often we've been taught or we've been raised on a 3 or a 5 or a 10-shot zero. And we have a significant amount of data now that shows that can work.
Oh, absolutely.
You can have a 3-shot zero, and those 3 shots, the mean point of impact of those, happens to properly line up perfectly with the actual mean point of impact of the total cone of fire of the gun. And in that case, you're going to be fine. But it can also not.
More than likely not.
Yes. And the more precision that the system shoots with, the smaller the cone of fire is, the less error you will experience. The bigger it gets, the more chance you have of a higher error occurring.
Right. And
a zeroing error is going to mess with you at every distance you shoot at. It's typically linear, and we'll talk about the linear, nonlinear errors here after we go through all of them. But typically, a zeroing error is going to show itself as if your zero is off by 0.2 of a mil at 100, it's going to be off by 0.2 of a mil everywhere, or half minute, or whatever units you're working with, angular units you're working with, in that will bite you everywhere.
Yep.
And so, being that we typically start with zeroing, right? We take a brand new rifle, mount the scope on it. The first thing we go do is zero it and gather muzzle velocity, right?
Right.
It's so important to get that right, because everything else that you do in the future, every target that you shoot at a longer distance is going to be based on that foundation. And if that foundation has errors, it's just going to compound and build in.
Yep.
So zeroing error gets lumped into the shooter category, although it is a mechanical thing, right? It's the relationship between a projectile's impact at a given range and the line of sight.
Mm-hmm.
The shooter is the one conducting that process.
Yeah.
That's why I lump it in there.
It's his responsibility. And I might be jumping ahead if you were going to mention this later, but I feel like that we've done a decent job of talking about this in our Ford Off podcast. So we've done several podcasts diving into Ford Off. Just using what we would traditionally call zero range, like zeroing your rifle at 100 yards, just doing that in and of itself, in my opinion, is a zeroing error. You're doing yourself a disservice because that arbitrary distance, say 100 yards, and your impact at such is only true for that specific set of wind conditions and temperature in some cases. And using zero angle will help. I mean, parallax has something to do with this as well, but using zero angle will help eliminate most of that error, and you will be accurately, air quote, zeroed no matter where you go in the world. And that's something that's, I think, grossly misunderstood. You go to any match anywhere, you go to the range, and everybody, I'm zeroed at 100, zeroed at 100, and most of them aren't zeroed at 100. It's probably 97 or 103 or something like that, very minusculely off. But the fact that they aren't accounting for the environment that they're shooting in, largely the wind's contribution to where that bullet lands, even as close as 100 yards, is an error, in my opinion, because it will create errors in your trajectory solution and in your cone of fire.
That's right. Yeah, and zero range is a problem in how it functions, and that means that the problem is universal across ballistic calculators. And you can display this to yourself if you set. I use an example in one of the classes I teach where I say, okay, we're in Alaska in the wintertime, so we're down at sea level. So set your air pressure to where it's similar to that. So 29.92 inches of mercury is standard sea level conditions for pressure. And then say it's 20 degrees out or 0 degrees out, right? It's cold. So high density air.
That's a pretty common day in Alaska.
At high pressure, right? So that we're all pretty aware, that's going to cause more bullet drop than the opposite. But for the sake of the example, set any ballistic calculator out that 29.92 inches of mercury, set humidity 50%, and set your temperature to 20 degrees. And tell it you're zeroed at 1,000 yards, which is possible, right? I shoot a 1,000-yard target. I'm hitting dead on. I slip the turrets to zero. That rifle is zeroed at 1,000, right? So you tell it you're zeroed at 1,000, and then you go to wherever it shows you your ballistic solution under those same conditions, environmental conditions. Scroll it to 1,000 yards. What is it going to show you? Zeroed at 1,000, right? Because that's what you told it. Now, take the temperature and increase the temperature to 80 degrees, and take the air pressure and increase it to, say, 22.
Decrease
Decrease it to 22.2 inches of mercury. So that would be like 8,000 feet. Pressures that are pretty common at 8,000 feet. If you take that rifle and ammo and you drive or teleport, whatever you want to do, right? Like there's no disturbance to the system. The scope hasn't been bumped. It hasn't been dropped. None of that stuff. The ammo produces the exact same velocities, right? And you simply take that and you go to Wyoming or Montana or Colorado in the summertime, you can be 80 degrees out at 8,000 feet.
Absolutely.
If you shoot that 1,000-yard target with that rifle set up the way it is, are you going to hit dead on at 1,000?
Absolutely not.
No way, right? You're going to hit high because the air is less dense. And you've also had a Mach number shift with the temperature shift, but just simply based on air density, you're going to hit high.
By a lot.
But then scroll to 1,000 yards and see what the ballistic calculator tells you. Shows you that you're hitting dead on at 1,000. Doesn't work. Now, there's all these modifications that have occurred with different ballistic calculators of atmospheric base zero and stuff like that, right? But the problem is that your bullet doesn't go wherever it ends up because you arbitrarily state it does. But the ballistic calculator, regardless of the type, only knows what you tell it in that input. That's the only input that thing has between all the math that's happening under the hood and providing you a solution. That's the reference point that connects the two. And so that's why we did zero angle, which fixes all that.
Yeah.
You don't have that problem.
No.
So, sorry for the aside there.
No, that's a perfect aside and a great plug for if you're one of those guys using one of the, the old school BC-based calculators, as pseudo advanced as they may seem, the app is free. Download the FortOff app for free and set it up with zero angle, and then compare it to your old BC-based solutions. And you can use your BC-based solutions for all your stuff, but then just compare back every now and then, and you'll find that a drag coefficient-based solution with a properly set up zero angle is just simply more right. It's just right. It's maybe not right is the right word. Maybe it's correct.
Yeah.
It gives you correct solutions where BC-based solvers don't all the time. And that's one of the big things that we've been trying to push. And I've said it many times, and I'll say it again here. Growing up in the long-range community, when I was, cutting my teeth with it, good data in, good data out. Everybody always said that.
Mm-hmm.
And with the BC-based solver, you put all the good data in that you have, and you still get the wrong solution. And that bugged me.
Mm-hmm.
And now with, drag coefficient-based solutions with ForwardOff, you put good data in, you get the good data out, and it's free. So check that out.
Yep. All right, so that kind of sums up shooter. So we've talked about muzzle exit. That's your randomized dispersion that you get of your shots.
Mm-hmm.
And that what you get at 100 is linear plus, right? It's going to get a little bit worse as the bullet continues downrange. Then we talked about the shooter and all the different. So you can, as a shooter, you can work to reduce your aiming error, manage your recoil better, have more consistent cant, be better at parallax adjustment. Just stop shooting when the mirage shows up. I'm kidding.
Yeah,
that's when
that's
you'll
what I
always
would
just
do.
have to deal with.
Just get a bigger target.
But the zeroing errors, if you're going to target anything in that list to try to improve the randomized errors that you have as a shooter, I would suggest, based on my experience, that you conduct zeroing in a statistically valid manner.
Absolutely.
All right, so next category is going to be wind. You said you had never heard of her.
No, I mean, I'm 1/4 inch MOA all day long.
That's right.
As long as I do my part.
As long as you do your part, which involves living in a location where wind doesn't exist, like K&M, apparently.
Yeah. Well, it did blow, but at that particular time when we were shooting, I was just like, this is unreal.
This is called wind?
There have been situations where I've made a no-wind hold at, say, 800 yards, but that situation wasn't actually no wind. It was one of those. It was very light and with my spin drift or whatever. Yeah. This was legit dead calm.
Yeah.
But that's a very, very rare instance, even at K&M. But the wind is, all jokes aside, it's always the fickle witch that always wins.
Right.
Yep.
And depressingly, Nebraska has 2 days a year where there's no wind in the springtime, and one of them is today. And instead of out there,
we're doing this.
Yeah, we're doing a podcast.
Yeah. Well, even if we weren't doing a podcast, you'd be working in a lab. You wouldn't be enjoying it anyway.
That's true. All right. So wind obviously causes, a horizontal deflection of our shots, right? Our groups start to increase widthwise because of wind speed and variation. And unfortunately, those two are wind speed and wind direction. Those two are always in a state of variation, right? And so we're always going to have a randomized shifting left and right horizontally of our shot impact location. But what's important here is that almost all of that left to right variance and impact location we see on target, we attribute to the wind, but it's not just the wind. It's wind and horizontal dispersion. Because when you shoot a group at 100 yards, you still have shots that are going right and left. And those shots are going to continue to go right and left. So the rightmost shot in your group at 100 is going to continue to be the rightmost shot in the group as you go to longer and longer distances, that specific shot. So you have to keep that in mind when you're making an assessment on, because we lay down and we shoot and we miss left or right. And our immediate assessment is, I misjudged wind speed or wind direction. It's actually this. And like when you use ForwardOff, what we recommend is you go in and adjust your wind speed and wind direction until they match what your bullet had for horizontal impact. The important thing to keep in mind there is that it is possible that the majority of that left or right that you had on target came from the raw dispersion piece if you don't understand, if you haven't done high enough sample size testing to get the true cone of fire of your gun, and you've done smaller sample size testing so you think it's better than it is, when you get that result of the shot that goes farther to the left than you expect based on your cone of fire assessment on a small sample size, you're going to automatically attribute that to the wind because you have no what else would do that. If the wind didn't cause that, you're going to adjust the ballistics calculator to say, this is the wind speed or direction that would have caused that. And then your next shot, it's going to throw you off because you're feeding in a wind speed and direction that isn't correct.
Mm-hmm.
The reason that shot impacted as far left as it did is because of the dispersion itself. So keep in mind that the horizontal impacts on target are a constant combination to variable degrees of wind and horizontal dispersion. Now, obviously, you can get some vertical dispersion from wind as well, aerodynamic jump. Yep. It's nowhere near the level that you get in the horizontal plane, right?
Absolutely. It is still pretty significant, especially at those longer shots.
Yes, absolutely.
And another plug for Fordoff that it can actually solve the physics equation involved to calculate aerodynamic jump, and any BC-based solver simply lacks the knowledge of the projectile necessary to calculate those equations. So it might spit you out an aerodynamic jump number, which is likely an empirical formula placed on it. And in my experience with BC-based solvers that produce an AJ number, they're grossly overstated, and you have to start doing funny stuff like, if you're really shooting an 8 twist, you tell it you're shooting a 10 twist, and your spin drift and your AJ numbers will line up a little better. Right. So you have to lie to the calculator to get it to work. Not the case with Fordoff.
That's right. Yep. Now, another area where the wind can get you is in the vertical plane that's not from aerodynamic jump.
Okay.
You know what that is?
I'm guessing vertical wind off a cliff.
Well, yeah. Okay. Let's say even on flat fire here in Nebraska where it's flat.
I can't say.
Head or tail winds.
Drag. Yeah.
Yeah.
Wind is a drag. Wind is based on drag. So if you're essentially increasing or decreasing the velocity of the bullet, that's going to change the drag.
Mm-hmm.
Okay.
So you'll generally see this beyond 1 to 1.5 second time of flight. So most stuff we're shooting, it's past 1,000 where you're going to see it start to show its head.
Mm-hmm.
But don't forget that. Just because the wind's blowing doesn't mean it's always left and right, that you can get vertical, an observance of a vertical difference in your shot impact because of it. So, but yeah, wind is always a booger. So here's another interesting one on wind.
It's not if I do my part.
That's right. So a common question that gets brought up is where is the wind most important?
Yeah.
What would you say?
I would say it depends, but largely I am not very astute, but I can measure wind speed at my location, so that's usually what I roll with. Try to watch mirage. I think as the target ranges become extended, the distance away from you, the wind speed at that location becomes more important because the bullet's spending more time in that environment because it's slowing down. It's leaving me at Mach Jesus, but at 800 yards, it's going much slower.
Mm-hmm. Yeah. So the answer to that question, where is the wind most important? You ask folks that, and they'll say, "Oh, at the shooter," or "Oh, at the target," or "Oh, in between." And you're correct in that it depends. Generally, at target distances where you're not even approaching transonic or subsonic flight, so let's say out to 500-800 yards from most of the stuff we're shooting, the wind is going to have the highest. The wind at the shooter's location is going to have the highest contribution. The wind is having an effect the entire way to the target, but the wind at that early wind, say from the shooter's location to 100 or 200 yards downrange, is going to have the majority of the contribution. So say you have 100 inches of wind deflection on target, of the wind that's at the first 100 yards might take up 30 or 40% of that, and then it just bleeds off.
Mm-hmm.
The wind at the target is the least.
Okay,
has the least input there. As the target range increases, the time of flight gets longer, you'll start to see more of a normalized effect of where the wind matters most. So usually, 800 to 1,200, 1,300. I'm talking in generalities here, right?
Sure.
The wind's there, or the target distance is there. The wind's going to kind of be equal in value in how much, your total wind deflection, how much of it comes from each range bracket. It's going to kind of be equal. And then as you push out past that and you start to go you transition through transonic and into subsonic flight, avoiding transonic gremlins, right?
Oh, gosh.
Anyway, have to address that at some point, too.
We did briefly, and when we talked about, was it Fordoff? I forget which podcast that was. We did talk about, in the literal 100,000 plus shots, we've recorded transonic instability twice.
Yeah, a couple times, yeah.
Yeah, 2 times, yeah.
But once that happens, right, once you're shooting into subsonic associated ranges, the wind is actually most important right there around the transition from transonic into subsonic flight.
Sure.
But anyway, so that question is a common one that gets thrown around. Where is the wind most important? And the answer is it depends.
Depends on if you do your part.
That's right.
SnapSafe modular assembly system locks the thick steel exterior together in minutes anywhere in the home. Featuring a pry-resistant 3/16" solid steel door, 8 1-inch chrome steel live locking bolts, digital or mechanical locking options, 9-gauge steel exterior walls, 2300 Fahrenheit 1-hour fire shield protection, fully adjustable shelving, and a lifetime warranty. SnapSafe, a modular safe with welded safe security.
All right, so that's category 3, right? So we did muzzle exit, we did the shooter, and wind. And we're starting to form the picture here of, I said, in muzzle exit, the shot that's most right in the group is going to continue to be the most right as a function of range.
Sure.
So if you happen to catch a left to right tailwind with that shot, it's going to cause it to go right even more. If you happen to catch a right to left tailwind, it's going to start to cancel some of that out, and that bullet's going to move back towards center some.
Mm-hmm.
Now, the shooter error piece is randomized in direction, right? But that could be additive. Let's say, let's stack those 3 just to start painting the picture. It's the rightmost shot in the cone of fire. You have a left to right crosswind. That's going to cause it to impact even further to the right. And then your aiming error, recoil management, whatever that list of shooter stuff was, is also biasing you to the right. That shot's going to go even farther to the right.
Airmailed one.
So you can start to see how they can stack or cancel depending on which one of those shows up for that specific shot. So now we'll move into velocity. So we've talked a little bit about like velocity and metrics and standard deviation and extreme spread and stuff like that. And standard deviation is really the tool to use from a hit probability standpoint, because standard deviation can provide you probabilities. And fortunately, although the shot distribution is not usually normally distributed, velocity is. And so that's great. That means we can take that standard deviation and apply that measurement to our average and get some probability-based stuff. So again, you have to have a sample size that's high enough to populate a bell curve for standard deviation to be useful. So a standard deviation on a 3 or a 5 shot group, you can happen to, just like you can happen to get a 3-shot 0 that perfectly matches the mean point of impact of the true dispersion cone of fire of that system, you can happen to get a 3 or a 5-shot standard deviation that is the same standard deviation as the total population. It's possible. It's also possible to be wrong.
Yeah.
And it's probably likely that
more
you're wrong.
probable that you're wrong.
Yeah. So when you're trying to understand your velocity variability and how that is going to play into the hit probability, you again need to have a sample size that is significant enough that it can populate a bell curve. Our data shows that around 20 plus, you can start to get there, right? Because you're also weighing, like, how many do I need to do to get a good number
versus
avoiding burning out my entire gun just to get a solid velocity standard deviation, right? That's the balance.
Yep.
So once you have that standard deviation, what it tells you is from your average, which you're also going to get an average velocity calculation from that information. From the average, if you go up 1 standard deviation and down 1 standard deviation, let's just say 2,700 foot per second average, and your SD is 10. So from 2690 down 10 to up 10, 2710. Between those brackets, about 66.7 or whatever percent of your velocities are going to fall within that. So now you start to have a probability of what to expect. So in simple terms, think of it as 6 to 7 shots out of 10 are going to have a velocity between those two brackets. If you go up or down 2 standard deviations, so that would be 2680 to 2720, that's going to encompass 95%. So 9.5 shots out of 10 are going to have velocities in those two brackets. And then if you go plus or minus 3, 2670 to 2730, that's going to be 99.7. Essentially, all of your shots should fall within those two.
Right.
So that's useful because I ran some numbers before we came up here. This is a 6.5 Creedmoor with a 140 ELD match.
Pretty standard.
Yep, 81500.
Yep.
Our old staple. Right?
It'll never catch on, really.
No.
Yeah, bad.
Yeah. But anyway, if we look at the effects of velocity, a 10 foot per second difference in velocity is going to cause a 5-inch shift in the vertical point of impact of the bullet at 500 yards.
Half an inch.
Half an inch. What did I say? 5
5,
inches?
yeah.
Yeah,
0.5.
0.5. Yeah, half inch.
I didn't do my part if it's 5 inches.
That's right. So in this example, there's all the bullets go in the same hole. There's no muzzle exit. Perfect bullet, perfect barrel. They all come out identically. No shooter error, no wind. Nothing else is happening. Just what does velocity variation do? When you get to 1,000 yards, that 10 foot per second difference in muzzle velocity is going to cause a 3-inch vertical difference in point of impact between those two. And when you get out to 1,500 yards, it's going to cause an 11-inch.
Nearly 1 foot.
Yes. And the reason that it's growing is because of time, right? The time it takes to get to 1,000 yards is long enough that the difference in those two is starting to show itself vertically. So velocity variation, you're not going to see a whole lot out to 500 yards. You can have pretty extensive velocity variations and not have a significant change in your point of impact on target. But the farther out you go, the more it magnifies. So now you can, and velocity is always going to affect you in the vertical plane, right? It's going to cause shots to go high and low. So you can start to add that into what we've talked about before. So before we gave the example of the rightmost shot in the group. Let's say it's the highest shot in the group. And the highest shot in the group is also combined with the shooter error causing it to go high, right? Your aiming error causes that to go higher yet. And then your wind, you have a strong tailwind at 1,000 yards, causing it to go higher yet. And your velocity, it's also the fastest shot of your probabilities. You caught the high end of the distribution and it's the fastest shot. That's going to cause it to go even higher yet. Now you can start to see why it gets so randomized in between, because you can have a shot that went high from muzzle exit, no shooter error, it's perfectly in the middle, no wind error, so those two don't contribute. It's just the shot that went high from muzzle exit, and then velocity is slow.
So now it's
and
right
that cancels out the muzzle exit, goes right to the middle.
Yep.
So it just depends on the value of those that you end up getting.
It's like stacking cups.
Yeah. Yep, exactly. So velocity is pretty easy to understand because we're so used to concentrating on it and measuring it. But just the thing to take away from that is, as you start to look at hit probability and using standard deviation as a predictive tool, make sure your standard deviation is based off of enough shots that it's a valid standard deviation. So the last one,
advice.
Yeah, the last one here is drag or drag variability. And I know, like you said, we just launched the DVRT technology and talked a lot about drag variability in that. So it's a novel concept to the shooting community at large. It's not a new concept in the field of ballistics. It's been around a long time. But drag variability, just like velocity variability, is normally distributed. That's good. That means we can use that standard deviation tool easily.
Which is, convenient.
Yeah. And it also affects you in the vertical plane, primarily is where you're going to observe it, but it also affects you in the horizontal plane. And the reason for that is wind deflection. I forget what podcast we described that in when we went into detail about wind, but
I think it was just on wind, wasn't it?
Was it?
Or external ballistics.
Yeah, maybe.
External ballistics, maybe part 2.
Yeah, I think so. But wind deflection comes from drag. If you don't have any drag, you don't have any wind deflection. And so where we're most going to notice drag variability is in the vertical plane at those longer time of flights, those longer distances. And so that Creedmoor example we had for what was 10 foot per second worth, I ran with a 2% difference in drag, that's going to happen in every 6.5 Creedmoor out there with every bullet. You're shooting 135 A-tips, like the most optimum drag variability bullet that you can get your hands on in aerodynamics, and you're going to have 2% drag variability. It's going to happen in total, right?
Yeah, your extreme spread.
Yep. You're going to have one shot that's 2% difference than another shot at some point in time. So a 2% difference in drag variability, this is ran with that 140 ELD match. At 500 yards, it's worth 0.3 inches. So it's even less than the 10 foot per second muzzle velocity variation.
Virtually bullet diameter almost.
Yeah. But at 1,000 yards, it's worth 4 inches. So it's now worth even more than 10 foot per second of velocity.
Nearly half a minute.
Yeah. At 1500, it's worth 24 inches, 2 feet.
That's a distance you can measure in feet.
Mm-hmm.
And in the world of precision shooting, that's
we don't like feet, you know.
Yeah, that's remarkable.
So you can have a little bit higher than average drag and a little bit lower than average drag. The stuff that's a little bit higher than average drag is going to cause shots to go low. It's higher drag, meaning it's going to take it longer to get to the target. So you're going to have more drop. And the inverse is true. The lower the drag is, the faster it gets to the target, the less time it has to drop, the higher it's going to hit in relation to those other ones. So now that's the fifth one. Now you can start to add all these things up. So we have, from a muzzle exit standpoint, it's the highest shot in the group.
All right, yeah, let's go in for an example. So in this example, you got a high shot because of muzzle exit.
Yep, it's the highest shot in the group. So that means it's also going to be the highest shot as we go downrange. But the shooter's aiming error on that shot was below the target by the same amount that the shot is high from muzzle exit. That's going to cause it to go right in the middle, right? Your aiming error has compensated for the dispersion. Shot goes right in the middle. From a wind standpoint, let's say it's a straight crosswind right to left. That's going to cause you to have a deflection to the left due to the wind. And because it's right to left with the right-hand twist barrel, aerodynamic jump is going to cause it to be slightly high. So now that bullet, which was high, was canceled by the shooter aiming error to be in the center, has now moved to the left due to wind and slightly high due to wind because it was a right to left crosswind. And the velocity of that shot was, on the upper end of one standard deviation, say 10 feet per second. And at 1,000 yards, it's going to move 3 inches higher. And then the drag of that shot was a low drag on the distribution of drag variability. It's on the low side of drag. Now it's going to move 4 inches higher than that. So you can kind of walk and see how that bullet got to where it ended up based on what the values and magnitudes were of each of these 5. Adding all those together is what gives you your hit probability. Because it's a probability because all of those have, again, different orientations and magnitudes. And so you really have to run the combination of all of those things that you possibly can to then see what your distribution looks like on target at distance.
Wow. That's a lot of things. I mean, I think of like a slide rule, where if you move this one slide rule, it automatically moves these other ones. Mm-hmm. And you've got 5 of them that all are going to stack onto each other. Some will be additive, some will subtract from it, and you only have control over some of these. Mm-hmm. And even if you control every variable you can, they all still exist to some degree. And when you're shooting stuff really far away, you depending on your cone of fire, what you think your cone of fire is and how big the target is, you can absolutely be making corrections that are just making things worse.
Yeah. Yeah, to your point at the FTW example, shooting the 7 PRCs, I mean, these are Creedmoor numbers that we ran here. So the 7 PRC with a 180 ELD ELD match is going to be more efficient than a Creedmoor with a 140 ELD match.
Sure.
So you could take these numbers and, trim them down a little bit, but
they're still there.
At 1,500, 10 foot per second was worth 11 inches, and at 1,500, 2% of drag variation was worth 24. So just those two, which probably you extend from 1,500 to 1,800, and these numbers are probably fairly representative of the 7 PRC you were shooting. If those two add in the same direction, high velocity, low drag, 35 inches.
Yeah.
And if they go the opposite direction, 35 inches. What's 35 plus 35?
A lot.
70.
70, yeah.
So you can have a 70-inch vertical just from two of those factors.
That's
no
almost
wind,
how tall I am.
no shooter error, no muzzle exit, right?
Yeah.
So you can start to see why when you really start stretching the limits, your hit probabilities can get quite low. Everything has to be as perfect as possible. Yep. But also why it's easy for you to lose sight of that the noise in the system is probably bigger than you expect. Because early on in my experience, I was aware of muzzle exit variability. I shoot a group at 100, even as a kid when I got my first rifle. I shoot a cardboard box and not all the bullets go in the same hole. Mm-hmm. That's probably lumped together with shooter error too, right? There's some level of both of those.
Even Jayden has some shooter error.
Oh, I got lots. Yeah. And I didn't know that when I was a kid, I didn't know that wind affected the bullet. I grew up in southern Colorado, windy all the time. But
yeah, you shoot.
Who would think that? I didn't know I didn't even know what velocity was, so how can I understand that it varies, much less drag, right? And so, but as you grow in this information and you start to understand these different attributes and you start adding them all together, I can no longer look at the patterning that I shot on that cardboard box at 100 yards and expect that to be what happens at longer distances, at longer times. That's ridiculous, right? It can't. And so I guess one of my goals in discussing this, on this format on a podcast is that I hope it helps people to grow past those early expectations you have. You just shoot a group on paper and you're like, okay, this is what this thing does. And then you go out at longer distances and it doesn't do that. And you start checking scope bases and you start checking action screws and you call into question whether your velocity is right or not. And you come back and re-zero. You waste all that time and money and confidence and all those costs we talked about.
Mm-hmm.
Hopefully they can start to avoid that and understand what makes up the hit probability, how to gather the information to start to have a better understanding of that. And then once you've established it, living within the noise of that system and improving what you can. So you can make improvements to the muzzle exit conditions by your load, right? You can have good shooting loads, bad shooting loads. You have the ability to have a hand in that. You can try a different load of ammunition. You can hand load your own stuff. When it comes to the shooter, you can work on reducing aiming error, recoil, all of that stuff can be improved upon. You can do a correct, statistically valid zero. In the wind, you can pay more attention there and start to learn and parse out how much is wind and how much is horizontal deflection. Velocity goes back to the type of ammo you're shooting, and drag, the type of bullet you're shooting. So you do have a hand at play in improving all of these different things. So hopefully that is helpful to folks, and they can look at that.
Well, I think even a lot of the advanced shooters are probably aware that all of these exist, but it's nice to give them, or everybody for that matter, a peek behind the curtain, or not necessarily a peek behind the curtain, but a look under the hood of how all of these factors work with and against each other. Because sometimes, I know velocity exists. I know drag variation exists. I know I have error. I know my wind. I mean, I'm really good at reading the wind, but
right.
That is a problem. I know muzzle exit exists, but to discuss all of them simultaneously and how they can work together to make problems, what seems like a problem, exist, or make it go away. Like, that velocity was the highest velocity that this load's ever going to record ever. It was the anomaly, the big outlier. But there were 2 or 3 other variables that worked against it, and it's in the center of the group. I never knew it even happened.
That's right.
And it's just cool to see how all of those are interlocked, essentially, again, because most of us are understanding that, all this stuff exists, but it's not talked about in uniformity and togetherness about how they actually interact. And I think that's going to be pretty well received, again, because it is technical in nature, and that seems to be what our audience likes. And timely, and I'm glad you mentioned it in the podcast, that we have wanted to do this podcast for a while, but you have to lay the groundwork to understand this. You have to talk about principal axis tilt, center of gravity offset. You have to talk about cant and zero angle versus zero range, and how wind deflection actually works, and talk about sample size, and in most recent, talk about drag variability. And for anyone out there who hasn't, definitely listen to the drag variability podcast. We shed a lot of light on that topic just as a concept, and then also what it means to you as the shooter. We compare it to a slightly more common term known as BC variability, and how those two things can be much different than each other. And then what products we manufacture that have this technology to reduce the drag variability. And you said you have control over that. You can choose products that have a known technology in them that help reduce the variability. But all in all, Jayden, I can't thank you enough for, I know you, like we talked at the beginning, you've got you could work 80 hours a week if you wanted to. Certainly shouldn't, but you've got a whole schedule full of things to do, and the podcast is something you squeeze in, but we certainly appreciate it as a community.
Sure. Yeah. Well, this one's cool because like you look at the DVRT stuff, the reason we made that discovery and were able to make the improvements on those bullet designs was because of this understanding. If we didn't have this, or this wasn't known, there's no way to isolate what's causing it. And it's also really cool. We have a method to test where, let's say I'm running the radar laptop, not even looking at what's going on, where the shooting is occurring. And let's say Jacob or Miles is shooting. The data that we record from that testing, I can take that data and figure out where that shot went without ever knowing where it actually went. And we're right about 95% of the time.
How cool is that? You don't even have to see where the bullet goes, but you can look at all of these variables. Obviously, there's some shooter-induced error that you can't control, but you can look at all your recordings and predict with 95%-ish repeatability that bullet went there because of these reasons.
Mm-hmm.
And it wasn't that long ago, that would have been a pipe dream.
And when I say 95%, I mean like let's say we take the data, we don't know where the shot ended up. We have it recorded, right? So we can compare it, but we don't know. All we have is the data that was recorded. We can say, all right, that shot went 10 inches high and 10 inches left. The actual positioning of that shot was 9.5 inches high, 9.5 inches left.
Yeah.
That would be a simple example.
Wow.
Of what I mean by that.
How cool is that?
It's pretty cool.
Wow. Well, I would say that's, just a testament to the actual testing, the actual R&D, the actual science that's going on here. And not everyone understands or appreciates that. But yes, we're just, some hayseeds out on the prairie in Nebraska, but there's real science going on out here, and that's cool to be a part of.
Absolutely.
So, Jayden, with that, do you have anything else that you want to talk about or summarize about hit probability?
I just encourage guys, we've had a lot of folks that have come back to us and said, hey, I shot my first 20 or 30 shot group ever.
Oh,
and
yeah.
Dang it if it didn't hit my ego a little bit,
Yeah.
but now I know.
Yeah.
And I did it again, and it did the same thing.
Mm-hmm.
And I've never had that happen when I shoot 3-shot groups or 5-shot groups.
Yep.
Like they're always different.
Yep.
Every time it's not repeatable. I don't get a stable result. I hope this topic helps people in the same way that one did.
Mm-hmm.
And hit probability is useful in a lot of places. It's not just competition. I use it for hunting.
Absolutely.
I check all these numbers and see what are the extreme possibilities. I take my group size, and then I run that out at distance, and then I add my muzzle velocity on top of it, and my drag on top of it, and then my shooter error on top of it, and then my typical wind uncertainty on top of it. And now I have a true concept of what the cone of fire is going to be, all things worst case, which is what I want to base my capabilities on, because I have to make a fast, efficient, ethical shot on that animal. And so if I understand all of that, I now know where those limitations exist. And I can not guarantee, because nothing's perfect, but I can more closely guarantee that when I decide that it's time to go, that the results of that are going to be in alignment with the goal.
Excellent.
If that makes sense.
Yeah, it absolutely does. That's exactly what this is for, is to make sure that you're going out there and you're going to hit what you're aiming at with high confidence, high probability.
Yep.
Awesome. Well, Jayden, thanks for coming on the show.
Sure.
Guys, thanks for tuning into this episode about hit probability. It was great to dive in to look at all the variables that dictate why a shot goes where it goes. We hope you enjoyed it, and we'll catch you on the next one.